a 1, but because the log is negative, it makes the 1 negative. So that point is 1, negative 1. And then for the third one, you have to get x to equal 3 squared. And 3 squared is also 9. So 7 plus 2 is 9. And then you convert 9 to 3 squared. And that would equal negative 2 because the log is negative. And so the point is 7, negative 2. And then the graph. Looks like that. And the asymptote is negative 2. The domain is negative 2 infinity, negative 2 to infinity, and then the range is negative infinity to positive infinity.
Any questions? So if you could put your T-chart back up. So the one question, I'm going to make you think a little bit. Maybe people can help John. She doesn't like to be put on the spot a lot. So if she has 3 numbers there, and I just want one more. And the number that I would like would be if we have the log base 3, and it's x plus 2. I want this number to be 1/3, because if we had 3 to the negative 1, then we have a negative exponent. So Jenna, what number could you plug in for x so that you have some number plus 2 makes 1/3? Right.
Negative. Hold on. 7/3, 9/3, 8/3.
Sabrina, negative 5 there.
I would have gotten there
Eventually, yes. So the reason I want you to use negative 5/3 plus 2, that makes a positive 1/3, because 1/3 can be written as 3 to the negative 1, which means that the x value in your t-chart, so underneath the 7, we could put a negative 5/3. Your y value would be negative 1, or it could be positive 1. But that then gets you that curve in your graph. So that kind of shows you where that curve starts to happen. So I'd like to have one of those numbers to have a negative exponent. So one of those numbers to be a fraction. Questions? Nice job, Jen. I'll just check it. Do you have the work on a different page?
For which? Oh, for the book.
Yeah, no.
Yeah.
You had I stopped back there. Okay, you're good. Nice job, Jen.
Miss King,
Yeah. Nope.
so I did number 5, it was f of x equals log 3 of 1 minus x. And then I found the one where it was equal to 3, so you had to plug in a negative 2 because 1 minus negative 2 was 3. And that equals 1, so then the x value is negative 2, y is 1. Then the next one you had to find the log 3 to 3 squared, and what is 1 minus what to equal to 9, which is negative 8. So you plug in the negative 8 and you get a 2 for that answer. And then I did the one where it was log 3, 1, and that was 0, and then that ended up being 0, so the common point was 0, 0. The asymptote is at x equals 1, the domain is negative infinity to 1, the range is negative infinity to positive infinity. That's the graph.
Any questions for Kate? Kate, can you just give your t-shirt? So Kate, I'm going to ask you the same question I asked Jeff. So what number could we plug in there so that it's some 1 minus a number would give us 1/3? So 1 minus 1 means 1/3. 2/3, yeah. So you could have an x value of 2/3, and then your y would be negative 1. So I want you to try and use that like fractional value so that you have a negative exponent of negative 1. So you would have 2/3 and negative 1 for another point. Nice job, Kate. So, like, this is your x. Even though it's not, it's x bar. It's on the right track. So any of these numbers are definitely out of one.
But you do your math.
Yes, so you're using just the product. So plug in your calculator.
For chemistry, I was doing 3 hours. How'd you do it?
Great, you're useless.
Better than a C. Better than a D. Alice, did you do better? Alice, did you get better than a D? What on what?
Yeah, barely hanging on.
Yes, I'm sorry. Here it is. Right here. I felt like I was in 3rd grade because they were way too simple. Well, I just can't be giving us problems that are way too simple because then we won't forget the basics for the test. And it's also really good whenever you're doing it during a study hall before class.
Yeah, yeah. Are there other questions that you have on the graphing? So the 6 graphing problems. Questions on those 6 graphing problems? How about questions on the book problems where you're using the properties and this property is supposed to be just equal to x, not a to the x. So any questions from the book problems? So today we are going to do section 3.3, which is more work with logs. Tomorrow we are going to review the 3 sections: exponential functions, logarithmic functions, and properties of logs. And then Friday we'll work on solving equations containing logs and exponents. So we need to know the properties in order to solve the equations, which is kind of what we're working towards. And you'll need your calculator just for one little problem. So I'd say for most of this, you don't really need a calculator, and I don't want you to rely on that calculator, unless it specifically says use a calculator. But some of them you just can't reduce or simplify without having that calculator there. So at the top of section 3.3, it talks about the change of base formula, which was created so that we can calculate logs that have other bases. So yesterday, and in your homework, in your notes, we evaluated the common log, which always has a base of 10. So in your calculator, you have that little button on the left side. You hit log. As long as the base is 10, you plug 4 in and you get an answer. So that's called the common log. It's the one that's in your calculator. Everything's kind of based off of that common log. We also, yesterday, used the natural log, because that has a base of e, and the calculator has 2.718 also built into it by pressing the little button on the side of your calculator. So, not all logs are common logs or natural logs, because down here we have the log base 4 of 30. And so the problem is, like, what happens if this number here isn't a 10? So it's not a common log if it's not a 10. And therefore you can't press that little button in your calculator. And when they didn't have calculators, they had, like, essentially they were semi-walking calculators, but they kept everything in tables, big tables. So like all the radicals they have values for: the square root of 2, the square root of 5, the square root of 7, the square root of 10. Like they have numbers all calculated way back in like prehistoric times, is what you're thinking. But, I mean, this is like a long time ago. And they pretty much had these numbers like already built in. And they had a chart that had base 10, common log. So they had all the logs figured out to the base of 10. So then they're like, all right, what happens if we change the 4, the 10 to a 4, how can we calculate that? So some crazy smart guy figured out that if you change the way this is written and take the log with a base 10 of 30 and divide it by the log with a base 10 of 4, because again, everything is kind of centered or based off of a common log, which means it has a base of 10. Then they could use their chart and calculate the value.
Why 30?
But it can be anything. I just picked 30 because 30 was in the problem. It can be anything. So your calculator is really great because my calculator is like almost prehistoric. It's like 1998 calculator. I don't have that fancy, wonderful button in your calculator that will calculate it without you physically doing this. But if you don't have that fancy, wonderful button, which I'll show you in a minute, this is how you would calculate the log base 4 of 30, or the log base 7 of 50, or the log base 2 of 25, whatever number you want to work with. So you take the log of the 30 divided by the log of the 4. Well, calculators have obviously come a long way. And there's a program in the calculator. So if you go to your fancy calculator and hit the math button, and if you press up twice, it takes you to log base. And if you hit enter, your calculator is now set up in a log with any base. So we can put the base as 4, and the number is 30, and then hit enter. My calculator doesn't have that special button. And in my calculator, I just have to type in the log of 30 divided by the log of 4, which still works. And it gives me 2.453 as well. But that's the program that's built into that function when you press that button. But it's enabling you to evaluate logs that have different bases. So the base 10 and the natural log, so the common log and the natural log, are these two buttons right here in your calculator. But the other one with the change, that base changing, now is also in the calculator.
So,
Brandon, I feel like every time I look at you, I think that it's Lent. Like, oh, he's been hashed. Because I feel like you have hashes on your head, but it's a sticker. It's not Lent, it's Halloween. We have like 6 months to go. Yes.
so if you were doing the log base 4 of 25, you'd have to do log 25 divided by log.
Exactly. Yep.
Okay, so it's not just a random number.
No. Oh, no. I'm sorry. I guess I thought you were just asking why I picked 30 and 4.
Oh, okay.
No, so it's not just a random number. It's the log of the big number divided by the log of the base.
Okay.
Sorry, I misunderstood you. Other questions? Which can happen a lot with Brandon. Alright, so we have a couple of properties we're going to look at. This really easy. There's really just 4 examples today besides that one, which doesn't count for the calculator example. So 3 properties of logs correspond with the 3 properties of exponents that we discussed on Monday. So the first property of exponent we said, if you're multiplying exponents and the base is the same, we said to combine them together, you add the exponents. Well, because logs and exponents are inverses, the property of a log says if you are multiplying 2 values together with a log, you can expand it into 2 separate logs being added together. So the log of u times v can be expanded into the log of u plus the log of v. So they're kind of similar, but because they're inverses, it's like you're doing the opposite. So with an exponent, our goal is to combine them together by adding the powers. With a log, you're actually splitting them apart by separating the 2 numbers. So they're like opposites of each other. So with the next one, we're dividing. Well, if we divide exponents, you really are subtracting them to combine them together. With a log, if you're dividing 2 variables next to the log, you're splitting them apart with subtraction. And then the last property we talked about was the power to a power property. And we said here, you're really multiplying the powers together. And that's similar with the log form. So if I have the log of u to the nth power, that nth power is still multiplication, but it goes in front of the log and it's being multiplied by the log. So if that was a 5, I'd have 5 times the log of u. So like the properties are pretty much similar because inverses are similar to each other. So underneath, there's a little example, and then we'll talk about expanding and condensing. This one should use the properties of logs to verify, prove, show, whichever word you like the best, that negative natural log of 1/2 is equal to the natural log of 2. So if you start on the left side, and we will be doing a lot of verifying as we work through trig. Essentially, there are 2 different ways, but there could probably be more than 2, but 2 common ways to verify that the negative natural log of 1/2 is equal to the natural log of 2. And I want you to try and use at least one of the properties from above. So how could we try and use 1 or 2 of those properties, Eris, to try and show it's equal to the natural log of 2? Yeah, so we can take this negative, because really it's a -1, and bump it as an exponent with the 1/2. So that would be the natural log of 1/2 to the -1. And Eris, what happens if you have something to the -1 exponent? Yeah, it flips and it becomes 2. So just by using that third property, if you have a number being multiplied in front of the natural log or the common log or the any log, it can bump up to be a power. There's another way we could think about this as well, Brandon. So this is way 1. What's a different way that we could try and simplify it?
The second one,
Okay, so the second one says what, Brandon?
the natural log of u over v equals natural log of v minus natural log of v, so natural log of 1 minus natural log of 2.
Yeah, I'm going to make these cursive looking so that the numbers don't look similar. So division really means you can separate it into subtraction. So he said the natural log of 1 minus the natural log of 2. Brandon, what is the natural log of 1 equal to?
What do you guess 2? Oh wait. 0.
0. The natural log is equal to 0. So the log basing of 1 is equal to 0. The natural log of 1 is also equal to 0.
I'm simplifying the whole thing.
It's okay. So the natural log of 1 is 0, and then we still have the negative natural log of 2, but the negative and negative become natural log of 2. That one's probably a little trickier because you have to use like 2 steps instead of 1. But it still works. So you can think of it as splitting apart into division and then simplifying the natural log of 1. But that's like a fact that you're going to see a lot. The natural log of 1. What is it? It's 0. The log base 5 of 1 is also 0. So you'll see that fact being used a lot, things you need to simplify. All right, so the other 4 problems, really short, straightforward day. Say to expand, which means we're writing it as a sum, a difference, or a constant multiple. That just means you have like a 3 in front. So you have 1 log. We're going to expand it using those properties into multiple logs, separate logs. So the log base 10 of 5x cubed y. Virginia, what would you do to try and expand that? So instead of saying times, it is being multiplied. So when we split it up, it becomes addition, right?
Do we have to write base 10? Or
No, and that was a question asked earlier as well. So you don't have to write base 10 if you choose not to. If it's not there, it's like it's invisible. So if the log isn't there, it's always assumed that it's base 10, even though assuming isn't a good thing. But if you don't want to write base 10, then you don't have to. But if it was a 6, Brandon,
You'd have to
then you'd have to write it. Because if it's not written, then it's assumed it's going to be a 10, which has a different value than a 6 or any other number. All right, so Virginia, is there anything else that we can do to expand this? Right. So it only goes with the x. It goes in front of that log that contains the x. So log 5 plus 3 log x because that was to the power of 3 plus log y. Questions? So the second one, we have the natural log of the square root of 3x minus 5, and then divided by 7. Alex, what do you think for me?
Well, you could use that second problem.
Yeah.
So it'd be ln the square root of 3x minus 5 minus 7.
Good. So minus the natural log of 7. Can you do anything else to simplify it?
Could you separate the square root?
So no, because like this is technically like grouped together as parentheses, but you can do something with the square root. Gonna have you phone a friend. Chelsea wants to help.
They can just multiply by 1.
So the square root is the same thing as having the natural log of 3x minus 5 to the 1/2 power. So the 1/2 power would bump in front, and we'd have 1/2 times the natural log of 3x minus 5. But that 3x minus 5, like that's grouped with one natural log, and it's kind of like contained together in parentheses. So if it was underneath a radical, they're grouped together in parentheses, so we cannot separate them. And then the natural log of 7. Questions? So that's called expanding. The last set of questions want you to condense. So we have multiple logs, and we want to pull them together in one log. And that's it. Like there is not a backside to this note. This is it. Couple examples. So half log base 10 of x, 3 log base 10 of x plus 1 in parentheses. And our goal is to condense. So Michael, what is it going to look like if we pull it together?
You could take the 1/2 and put it to the x and to the power of x.
And
And then you could do the same thing with the 3.
And again, if you don't want to read the 10, that's fine. And then what does your answer look like, Michael?
And then I had log. I didn't really finish, not gonna lie. I didn't really
That's
start.
all right.
And then you,
So what would you do with the x to the 1/2?
you just.
How can we rewrite the exponent of 1/2?
Oh, that's weird.
Okay, so we can make this a square root of x. And then, Michael, if it is addition, and we want to pull them together, what would it become?
X times. Would be x plus 1
And then that x plus 1 you said was
cubed.
cubed. So addition can be condensed together by multiplying the terms that were next to these separate logs. So you're pulling them together by multiplying those terms. So physically, you don't actually have to do the multiplication. We have a square root of x and then x plus 1 cubed.
Could you technically like pull the cubed into the problem if you really
What do you mean?
wanted? Like if you like put them like in factor, not like
Yes.
yeah.
So if you wanted, so it doesn't distribute, that's what I was afraid.
Yeah.
But if you wanted to, you could multiply all 3 of them together and then distribute the radical through, but it's considered to be simplified if it's factored, so you can leave it like that. Other questions? All right, how about letter B? We have 2 natural log of x plus 2 minus natural log of x. Plus. Okay? Nice, and I like how you said that. So the natural log, when you're writing it as division, it doesn't go in the top of the fraction, it doesn't go in the bottom of the fraction. It gets pulled out to the left because that's the function. You're not dividing the function. You're dividing the variables, the terms that are with the function. So it gets pulled aside to the left, and it's just the terms that are next to them that then you're dividing. So x plus 2 quantity squared divided by x. Questions? That's it. Your homework, there is no graphic tonight. Yay!
Yay!
it is in the book. The book is over here, so feel free to take a picture of it. And then how about a volunteer to do 61?